Hello everybody, and welcome back to this installment of Chapter 0 of the Damage Control Assistant Senior Enlisted Curriculum. I am Lieutenant Timothy Mueller, and I'll be the instructor on this lesson on the Center of Buoyancy. So now that we've seen the objectives for this lesson, let's take a look at the definition of buoyancy and the center of buoyancy. Buoyancy itself is an upward force exerted by a fluid that opposes the weight of an immersed object. B, which is what we're going to call the center of buoyancy, just like G from the last lesson, the center of gravity, is the point through which buoyancy acts. An example of this is boats, which have a force of buoyancy that's caused by the water that they're immersed in, and balloons. Balloons have a force of buoyancy that's caused by the air around them. Air and water are both fluids, and a fluid always, by definition, exerts a force of buoyancy on whichever object is immersed. So now that we have the definition of buoyancy and center of buoyancy out of the way, we're going to take a look at an equation for pressure. From pressure, we're going to be able to find out the overall force of buoyancy, and then from there, we're going to be able to find out the center of buoyancy. So to the left of the screen, we have this equation here. P equals the Greek letter rho times G times Z. P is the force of pressure. G is the gravitational constant, which for English units will be 32.2, and for metric it'll be 9.81. Z is the depth from the surface, or the depth from where the pressure is zero. And then rho is going to be density. Density is measured in mass per unit volume, such as kilograms per meters cubed. All right, now that we have that equation for pressure, I've rewritten it on the right side of the screen here. Let's take a look at what it would look like on a diagram and get a visual concept for what we're talking about. So here's this large tank. There's the bottom of the tank here, left wall of the tank, and then you have the water line. This is where pressure equals zero. You'll see a linear line down here with arrows. The magnitude of these arrows corresponds to the magnitude of the force of pressure. If we look at the equation for pressure, rho, the density of water, isn't going to change very much, especially when we're talking about surface warfare ships or anything that floats on the surface. G isn't going to change. It'll either be 9.81 for metric or 32.2 for English. Z is something that is going to change depending on how deep we are. So we can think of it as P equals some constant times Z, which gives us a linear relationship between pressure, which is the magnitude of the arrow, and depth, which is how deep we are. As you can see, we have three immersed objects in this tank, all of them showing different ways that pressure reacts onto different surfaces. We already saw that pressure rises linearly with Z, Z being the depth. Another note about pressure is pressure always acts perpendicular, or another word for that is normal, to a surface. So in this first example, we have a square. A square has one side on top, one side on bottom, and two on the sides. On the very top, we have a pressure that corresponds to this magnitude here. Then on the bottom side, we have a pressure that corresponds to this magnitude here. So we have a lot more force on the bottom that's pushing up versus on the top that's pushing down. Everything on the sides, they have the same linear slope as we have over here. However, each arrow on this side cancels out with another arrow here. So as long as that square doesn't crush like an aluminum can, then there will be a buoyant force due to the difference in the pressures from bottom to the top. The second shape that we have here is a triangle. So like the square, the top side has a constant pressure which is pushing down on the triangle. However, instead of having three sides, two of which cancel out, we have two sides, each of which are increasing in depth, so the magnitude of the pressure is increasing as we get deeper, but it's also angled, so it's not directly up, it's not directly to the side, it's angled. So we can see here, if you kind of picture these arrows, each arrow has a vertical and a horizontal component to it. That's on the left side, and this is on the right side. So if you look at this arrow here, because at this point, the magnitude of this arrow is the same as the magnitude of this arrow, and it's also, we'll just say for example's sake, they're at the same angle, that the horizontal components are the same. So we can look back at the square example, and it's the same type of relationship, where this one cancels this one. Similarly, the horizontal component of this arrow cancels out with that one. So now all we're left with is the vertical component of these arrows, which is providing that buoyant force for the triangle to hold it up. Now let's move on to our last example, the circle. This circle is located at a depth a little bit deeper than the square and the triangle. So the arrows for the circle are going to be a little bit higher in magnitude than what we saw for the square and the circle. So this circle, we have a top portion, which is located at this depth, which is going to have approximately this magnitude, not drawn to scale. And then we have the bottom, which is located right around here, which is going to have a larger magnitude than what we had at the very top. So this is a circle, which is 360 degrees. And since all the forces act perpendicular or normal to the surface, this means that at the top, and only at the top, will there be a straight vertical force pushing down. Similarly, at the bottom, and only at the bottom, will there be a force of pressure acting directly up. On the left and the right sides, and only precisely at those 90 degree and 270 degree points, will we have forces that are purely horizontal where they cancel each other out there. Everywhere else, we're going to see, just like we had in the triangle example, vectors that have a horizontal and a vertical component. So we'll see here, and we'll take these two arrows for example. This arrow has a horizontal component and a vertical component up. This arrow has a horizontal component to the left and a component up. These points are at the same depth, so the magnitude of these vectors is going to be the same, and also the angle is going to be the same since we have a circle. This means that the horizontal components of this arrow and this arrow are going to cancel each other out. However, the vertical components are both pointing up, which means that this is what's going to provide the buoyant force for our circle that's at this depth. So now we see how pressure acts. Where is B? Where is the center of buoyancy? Well, the center of buoyancy is going to be located at the geometric centroid of the submerged volume. In naval architecture and actual ship stability, this is a very difficult concept for someone to just measure, especially with pen and paper. However, we can use basic shapes and models to get a good approximation of where we are. We're going to start with the square. The centroid of a square is just in the exact center of that square. So with each side being the same length, defined as L here, the x-coordinate of the centroid is just L over 2, as well as y from the bottom left is going to be L over 2. Now we move on to the rectangle. Similar to the square, it's just going to be at the exact middle. However, the length and the height are different values. So the x-coordinate of our center of buoyancy is going to be L over 2, defining L as the long end. And then y, similarly, is just going to be h over 2, h being the height of that rectangle. Now triangles can be a little bit tricky, so kind of try and follow me through this. This is a little tip that I always used when I was trying to remember centroids of triangles. Especially for right triangles, you can have, if you look horizontally, you have the little end, the pointy end, and then you have the big end. The centroid is always going to be 2/3 away from the point, or similarly 1/3 away from the big end. So vertically, we have this right triangle. We see here's the point and here's the big end right here. So we're going to be 2/3 away from the point here, or 1/3 away from the big end. So here you see x equals 2/3 of L. Similarly, since it's a right triangle, we do the same thing but only in vertical. So vertically, we have the big end here and we have the pointy end here. So now we're going to be 2/3 of the way away from the pointy end, or conversely, 1/3 away from the large end. So y, measured from the top, so we're going to be 2/3 away from the pointy end. This gives us y equals 2/3 of h. If you didn't like that tip or that explanation, here's how to find the actual geometric centroid of a triangle. So here in this equilateral triangle that I drew, I've marked out the points that are exactly in the middle of each side. This is relevant for every single triangle. So if you mark these sides, you have these 3 points, and you draw a line from each point to the opposite angle. So from this point to the opposite angle, and this point to the opposite angle. Where these 3 lines meet is going to be your geometric centroid of that triangle. So here in the right triangle, I'm just drawing another one. I did the same thing. Took the points that are halfway on the sides, and I drew them to the opposite angles, and we get the intersection right about here. So if we look here, it falls. Now remember, this isn't drawn perfectly, so a little bit of difference in scale. However, we can see that's actually pretty close to about 1/3 away from what I said, the big angle. So here's our Y, and here's our X. This X here looks just about to be 1/3 of the entire length, and Y similarly looks to be about 1/3 of this entire length of the big side. All right, now that we're done with the lesson, let's go over a quick little explanation as to why buoyancy is important with a ship. Well, obviously it keeps a ship upright, so I'm going to go through two little examples of what happens to buoyancy as we change conditions on a ship. So the first example here to the left is we're adding high weight. At the top here, we have just a general vessel with a center of gravity above the center of buoyancy. If we add, say, 100 long tons to the very top, we learned in the last lesson that the center of gravity is going to shift up to a weight addition or shift down if we add it low. In this case, we added it high, so the center of gravity is going to shift up. We added weight, so we know that the ship is going to get a little bit heavier, so it's going to sink further into the water. That's going to cause the waterline to move up a little bit. Similarly, you can think of that as we're adding, kind of like a rectangle with this hull shape, we're adding a little bit of a rectangle of buoyancy to the submerged volume. So now that centroid of that volume has to move up in response to adding that weight. So the center of buoyancy goes from B0 right here to B1. Now let's take a look at a second example. Here's a vessel doing underway steaming, center of gravity on the top, and center of buoyancy at the bottom, just like we had in this example. Now it's subject to an immediate 100-knot wind on the beam. It's going to get pushed over, and then we're going to see if the boat is actually going to be able to right itself. So when it gets pushed over, that submerged volume changes shape drastically, which means the center of buoyancy is going to shift. If we assume that no cargo, no liquid loads change on the ship itself, then the center of gravity is going to remain the same along that center line. However, the center of buoyancy is going to shift over, in this case, to the right. So now we have the center of gravity pointing down, the force of gravity acting down through the center of gravity, and the force of buoyancy acting up through the center of buoyancy. You can see here we have what's called a righting moment. And we'll get into that in future lessons. However, you can see that as one arrow points up, the other one points down, it's going to want to cause to rotate it that way and return the ship back to the equilibrium on the center line. You can also take a look at this. Instead of keeping the waterline constant and having the ship roll about the waterline, you can view it in a more inertial frame by having the boat stay constant and have the waterline move around it. So here's the waterline originally. This is just the boat steaming away, no issues. Then it gets hit with this wind. The waterline moves to this angle here. So originally we had this triangle as well as this shape here was all submerged. That's what was contributing to buoyancy. However, now with waterline 1, this shape is still submerged. However, this triangle that I've hashed out here is submerged, whereas this triangle is not submerged. So we're shifting the buoyancy from this triangle over to this hash. Also, it's going up a little bit. So the center of buoyancy is going to move to or in this case, to our right, as well as up a little bit. And you'll see at different angles, that center of buoyancy will swing through an arc. This arc is very special in naval architecture. It has a center called the metacenter, and it's something that's very critical to giving proper reports to a commanding officer or to a chief engineer or an engineer officer on board. I hope you enjoyed this lesson on the center of buoyancy with regards to ship stability. In the next lesson, we'll be talking about the specific weight, specific volume, and density of saltwater, freshwater, and diesel fuel, so we can find out how taking on fuel or taking on water and damage can affect ship stability.